In this crash course of reviewing probability, we're going to look specifically at discrete random variables and the binomial distribution. So a good chance you may be using some of these formulas, so have your formula sheet ready. Let's look at a distribution of a discrete random variable. So when I just say discrete, I mean that your outcomes are 0, 1, 2, 3. There's no decimals in between. You're getting that specific discrete value. So it says, let y denote the number of broken eggs in a randomly selected carton of 12 store brand eggs at a certain market. Suppose that the probability distribution of y is as follows. So you're given this. Common thing to do is have to fill in an unknown value. So the idea here is that probability distributions will always sum to 1. So find your sum. When I add these values together, I get 0.99, so my missing value is 0.01. And then I'm going to start answering my questions. And the first one is, what's the probability of getting a 4? So we just answered that. That would be 0.01. Next, we're told to calculate the probability that y is less than or equal to 2. So that this means the probability that the carton contains at most 2 broken eggs, and then we're to interpret that probability. So that means that we would sum the values less than or equal to 2, so those probabilities are 0.65, 0.2, and 0.1, which adds to 0.95. So my interpretation is that 95% of the cartons contain at most 2 broken eggs. Next, we're told to calculate the probability that y is less than 2. Well, that's just 0.65 plus 0.2, which is 0.85. And then it says, why is it smaller than the probability in part B? Well, it's because it doesn't contain the probability that y equals 2. In part D, it says, what is the probability that the carton contains exactly 10 unbroken eggs? So when you look at this, you might be thrown off because it doesn't go up to 10, but watch that word unbroken. This is the number of broken eggs. So if it has 10 unbroken, that means there would be exactly 2 broken. So the probability that y is equal to 2 is exactly 0.10. Then it says, part E, what is the probability that at least 10 eggs are unbroken? So at least 10 would be 10, 11, or 12 unbroken. But again, my distribution is in broke eggs. So what does that correspond to? Well, 10 unbroken would be 2 broke, 11 would be 1 broke, and 12 would be 0 broke. So if we look then at this would be the same, that the probability is y is less than or equal to 2, and we did that above in part B, so that's 0.95. In part F, we were asked about the expected number of broken eggs per carton, so you probably want to take a look at your formula sheet. Giving myself a little more space here. Here's the formula for expected value in discrete random variables. So mu of x is equal to the expected value, which is equal to the summation of each random variable times the probability of it occurring. Therefore, I can say that, and I'm going to use y because that's my given random variable. I'm going to say that mu of y is equal to the expected value of y, which is the same as taking each individual probability, so 0 times the probability, each random variable times the probability of it occurring. And when I type this in, I get that my expected value would be equal to 0.56 eggs. I'm going to remind you of what that would interpret to. And it means that if we inspected many egg cartons, we would expect to see about 0.56 broken eggs on average. And now we're going to talk standard deviation. So let's take a look at what that formula is. And on your screen, you see the formula for standard deviation of a discrete random variable. And what does this formula mean? It means we take each observed minus our mean, which we just calculated to be 0.56, square that value times the probability of it occurring. So our first one, and I'm just going to open up a big square root symbol here. Our first one, random variable value that it takes on is 0 minus 0.56 squared times the chance of that occurring is 0.65 plus 1 minus 0.56. Square that times the chance of it occurring is 0.20, and I'm just going to put plus and an ellipsis up to the last one. 4 minus 0.56, square it times the chance of it occurring, 0.01. And I'm just going to enter this into my calculator. And when I do, I get approximately 0.898. So let's talk with this how this would interpret. My interpretation is if we selected a random carton of eggs, we would expect the number of broken eggs to vary by 0.898 eggs from the mean of 0.56 eggs on average. Okay, just as a reminder, you can calculate the expected value, the mean and the standard deviation using one variable stats. And the way you do that is pick a list like L1 for your random variable and L2 for the probability of it occurring. And then you run your one variable stat and you put L1 as your list, but where it says the frequency, you put L2. And it gives you both your mean and your standard deviation. So I encourage you to pause the video and try that. Another thing you might be asked to do is to describe the probability distribution. You could quickly make a histogram as well then, using L1 and L2, that same list. Set your width of each bar, the X scale, to be just 1, because each contains just one value. And you'll see your histogram, which hopefully you can tell just by looking at this that it would be skewed right. So, you would talk about that. You'd say the histogram is skewed right. The center has a mean of 0.56 with a standard deviation of, so you're talking your center and your spread. And, using all those words in context then. Let's move on to the example of the binomial distribution, which is a special form of a discrete random variable. I'm going to remind you of the acronym BINS and what that represents. We use BINS to check if something's binomial. So B stands for binary outcome, so like a probability of a success and a failure. I means each trial is independent. N is fixed in advance. So it's like you have X number of successes in N trials. And S at the end stands for we need to have the same value of P for all the trials. All right, so the example here is the AP Stat exam includes 40 multiple choice questions, each with 5 answer choices. Suppose you believe you have forgotten everything and must guess randomly choose one of the 5 answer choices on every question. Let X represent the number of correct responses on the test. Okay, so what kind of probability distribution does X have? So X could equal, you could have 0 correct, 1 correct, 2 correct, 3 correct, 4 correct, all the way up to 40. So we have a fixed number of trials. So X follows a binomial distribution, and you always want to state your parameters. And if you forget what parameters you need, you take a look at your formula sheet, and it tells you that N and P are your 2 parameters. So N is equal to 40 trials, and P would be the probability of guessing correctly. So the 1 out of 5 chance or 0.2. So our trials would be independent if you've truly forgot everything, which is not the case of anyone in this class. All right, what is your expected score on the exam? So go to your formula sheet and find the mean or the expected value of a binomial, and you should see that mu of x is equal to n times p. So you're going to do 40 times 0.2, and we would expect 8 correctly answered problems. And you're going to get way more than 8 right. All right, compute the variance and the standard deviation of x. So remember, variance is just a standard deviation squared. So let's do the variance first. So from the formula sheet, it actually gives us the standard deviation. So if I add a square and I square both sides, it would be np times 1 minus p. This would be my variance. And if I substitute in, that would be 40 times 0.2 times 0.8. So my standard deviation is, my variance is 6.4. And now my standard deviation would be take the square root of 6.4, and that is approximately 2.529. What is the probability that you will get exactly 25 questions correct? So correct notation here, if you look at your formula sheet, the probability that x is equal to 25, exactly 25, is equal to a combination from 40, select 25, because it could be your first 25 right, your last 25 right, the first 24, the last one. There's so many different combinations of how that exactly 25 could play out. So times the probability of a success raised to the 25th power, and a failure to the 40 minus 25 would be 15. Okay, so you can compute this on your calculator, but I'm guessing most of you would bypass that and go to the calculator command binom PDF. So remember, there's PDF and CDF. We're using PDF here because it's for one discrete value of 25. So you would show me your values, that n is 40, p is 0.2, and x is 25. And that produces a small number, very close to 0. So very, very low chance of getting getting exactly 25 right by pure guessing on this challenging exam. Okay. Part E. Overall, you believe you can do really well on the free response section. You did not study for the multiple choice section because you figured out that you probably only need 16 questions correct to earn college credit in the course. What is the probability that you correctly answer at least 16 problems? So this is saying the probability that your random variable is greater than or equal to 16. Well, I want to remind you that in your distribution, it goes all the way up. And I'm just going to go like this, 15, 16, 17, all the way up to 40. Okay, so greater than or equal to 16 would be 16. Oops, I didn't mean to erase there. Struggling with my tools. It'd be 16 through 40 is what I'm trying to say. But the CDF function starts at 0 and sums from the bottom of your list upward. Okay, So using this, I'm going to say that this is equivalent to 1 minus the probability that x is less than or equal to 15, or 1 minus binom CDF, so I don't have to write that formula out over and over, or sum it for 0, 1, 2, 3, all the way up to 15. The cumulative density function will do it for me. So n equal to 40, p equal to 0.2, and my x equal to 15. And I take a second, type that in, and I get approximately this as my probability.